For the last part of our review over some topics in general chemistry, we're going to look at intermolecular forces. When we start studying different types of organic compounds and looking at how their solubility varies, their boiling points, densities, melting points, all kinds of different properties that they have, it usually depends upon their intermolecular forces of attraction. So when we looked at different molecules as being either polar or nonpolar, we were able to determine what types of IMFs were present. And there were three major types. So dipole-dipole interactions, which occurred between polar molecules. Hydrogen bonding, which was a very specific type of dipole-dipole interaction, where we had a hydrogen bonded to a very specific electronegative atom. And then dispersion forces, called London dispersion forces. You might even seen them called van der Waals interactions. Those were present in everything, but they're the only intermolecular force in nonpolar molecules. So starting with dipole-dipole interactions, the first thing you have to have if you're going to have a dipole-dipole interaction is you have to have a molecule that's polar. So it's important to be able to draw a Lewis structure and then analyze it and see if the molecule is polar or not. If it's nonpolar, it's not going to have dipole-dipole interactions. And what happens is, in a polar molecule, that partially positive end and partially negative end will align in two different molecules. So they will orient themselves in such a way that partial positive aligns with partial negative aligns with partial negative, and so on and so forth. So the more polar a molecule is, the stronger its dipole-dipole interaction will be, or the stronger the strength of its dipole. You might see the symbol mu to represent the strength of a dipole, and they actually will give it a numerical unit. We won't calculate that, but you can actually see that number and look it up for different polar molecules. So if we look at acetone, which acetone is actually a ketone, is the type of functional group, which that means it has a carbon-oxygen double bond in it. And we'll learn functional groups in chapter 2. It is a polar molecule, so it will exhibit dipole-dipole interactions. There is one end that is partially positive, and that happens to be the end of the carbon. And there's one end that's partially negative, and that's the end where the oxygen is. So oxygen is more electronegative than carbon. And so that means that there's a difference in that electronegativity. Those electrons are pulled more towards the oxygen, and so it ends up developing a partial negative charge. And so in a sample of acetone, which is essentially nail polish remover, those partial positive and partial negative charges between different molecules line up. So notice the partial positive on another acetone molecule is lined up with the partial negative of one. And then going on, the partial negative is lined up with the partial positive of another molecule. And that's how they orient themselves, like these little magnets of just positive and negative charges. So positive, negative, positive, negative, positive, negative. But in order to have dipole-dipole interactions and have that lining up, you have to have a polar molecule first and foremost. So what we just talked about would have been something you learned in general chemistry. So now let's kind of compare how melting points and boiling points change depending upon dipole-dipole forces being present or not being present. So in something like acetone, which we just looked at on the last slide, we saw that that does have dipole-dipole interactions. So it is a polar molecule. We have that partial negative charge on the oxygen and a partial positive charge on the carbon bonded to the oxygen. Comparing that with something like isobutylene, which don't worry about naming these yet, we'll learn that later. That is a compound that's made up of all carbon and hydrogen. And if you recall, the delta En, or the difference in electronegativity between carbon and hydrogen, is essentially zero. So these types of compounds are going to be nonpolar overall, because all they have is carbon and hydrogen in them. And so it doesn't have dipole-dipole interactions. The only type of intermolecular forces present in this isobutylene would be London dispersion forces, which we'll review in a moment. So comparing now their melting points and boiling points. The isobutylene has a melting point of negative 140 degrees Celsius. And the polar acetone has a higher melting point with 95 degrees Celsius. So that polar molecule, it being polar, increased the melting point. Same thing with the boiling point. The nonpolar isobutylene has a boiling point of -7 degrees Celsius, and the acetone's boiling point is 56 degrees Celsius. So it increased the boiling point. We see an increase in those properties as we go from nonpolar to polar. Next, we'll look at hydrogen bonding. So hydrogen bonds are really just a special type of dipole-dipole interaction. We specifically have a hydrogen atom that is bonded to either an oxygen, a nitrogen, or a fluorine atom. Those are the three most electronegative atoms on the periodic table. If you look in the upper right corner, you'll see all three of them there. So really a hydrogen bond is just an extra strong dipole-dipole interaction. And so they're extra strong because the partial positive and partial negative charges are large. They're larger due to that really strong hydrogen bond that's present. So the analysis is just like we did last time. For example, if we have water, you have a partial positive on hydrogen because hydrogen is less electronegative than oxygen, which it's bonded to. And the oxygen will develop a partial negative charge. And so in between two water molecules then, this dashed line would represent our hydrogen bond, that intermolecular force. That partial positive on one molecule lines up with the partial negative oxygen on another, and that'll continue. So technically you can form two hydrogen bonds per molecule because you have two partially positive hydrogens on something like water. Something like an alcohol, you could only form one because an alcohol would only have one hydrogen on there. So it just depends on the molecule and how many hydrogens are attached to determine how many hydrogen bonds you could actually form per molecule. We can also look at something like ammonia, which is NH3. We have a hydrogen-nitrogen bond. So nitrogen's more electronegative, partial negative. Hydrogen's less electronegative, partial positive. That hydrogen bond will form between a partial positive hydrogen of one molecule and the partial negative nitrogen of another molecule. So that represents our H bond, that dashed line. And every single hydrogen is technically partially positive, and the nitrogen partially negative due to its greater electronegativity. So your ammonia could form even more hydrogen bonds because you have three hydrogens on there. Explain why the following isomers have different boiling points. Isomers are molecules that have the same chemical formula, but different structural formulas. So these are really good to compare to get an idea of how hydrogen bonding impacts the boiling points of molecules. On our far left, we have trimethylamine. So notice the nitrogen in the middle is not directly bonded to a hydrogen. All of the hydrogens you see are bonded to carbon. So this has 0 hydrogen bonds in this molecule. And our boiling point is 3.5 degrees C. And then moving over, we have ethylmethylamine. And here we have 1 hydrogen bond. Our nitrogen is directly bonded to 1 hydrogen. And our boiling point increased to 37 degrees Celsius, so it went up as we added a hydrogen bond. And then moving on to propylamine. In propylamine, we have 1 hydrogen bond here and another right here. So we have a total of 2 hydrogen bonds. And notice our boiling point jumped up to 49 degrees Celsius, so it increased even more. So the number of hydrogen bonds also will tell you how strong of a dipole or how polar of your molecule it will be. And boiling points and melting points will increase as the polarity of molecules increase. The last thing we need to review is London dispersion forces, or LDFs for short. So LDFs are a result of the constant random motion of the electrons that are within molecules. And so even if you have a nonpolar molecule, the electrons are not always going to be evenly distributed at any moment in time. So because electrons are in motion, there is a possibility that they will shift at one point and create something called an instantaneous dipole. So that temporary dipole that forms from the movement of those electrons is referred to as an instantaneous dipole. And then if you form an instantaneous dipole in one molecule, you can cause another dipole to form in a neighboring molecule. So imagine that in the picture on the left, we have Cl2, chlorine gas, and technically the difference in electronegativity between each of the chlorines is 0. So the electrons should be perfectly in the middle, and technically we would have no partial charges because it's a non-polar covalent bond. But at any moment in time, those electrons can move and shift. And let's say that they shift closer towards the chlorine atom on the right-hand side. Well, now if they do that, that chlorine on the right will develop a partial negative charge. The one on the left that's left without a little bit of that electron density develops a partial positive charge. And if this happens to be next to, which it would be, another chlorine molecule where it's non-polar, that can cause those electrons in that one next to it to shift in exactly the same way, where we have one end of the chlorine molecule that gains a little bit of extra electron density around it, becoming partially negative, and the other one being left without some, that's partially positive. So that's called an induced dipole. When you have London dispersion forces from an instantaneous dipole causing it to happen in a neighboring molecule. So induced versus instantaneous. And so basically you end up having an arrangement of your molecules that sets itself up just like it would in a dipole-dipole interaction, like the little magnets, only it's happening in specifically non-polar molecules. And these temporary dipoles are not anywhere near as strong as the permanent ones that are in polar molecules. So London dispersion forces are typically weak when compared with polar molecules that have dipole-dipole interactions or hydrogen bonding, but they can become strong, and it depends upon the molecule. A couple things that impact the strength of a London dispersion force is the size. And when I say size, I mean how many atoms are in that molecule, which the greater number of atoms, the greater number of electrons there are. So the bigger the molecule is and the more complex it is, the higher those London dispersion forces will be because the more those electrons can move around and shift about. Also, the surface area impacts the London dispersion forces. So is it a straight, long, linear chain, or is it a branched, smaller chain? Those things that will impact the shifting of electrons. So the higher the surface area is, the greater the London dispersion forces, and the bigger the molecule is, the greater the London dispersion forces are. So if we look at something like butane, so butane is an organic compound, and its formula is C4H10. It's the primary component in lighter fluid. It's made of completely carbon and hydrogen. So overall, butane is a non-polar molecule, but it will form London dispersion forces. So even though it's all carbon and hydrogen, if we look at this potential map of it, we can see that one molecule end has a bunch of partial negative charges that developed around that end of carbon and hydrogen. And the other end of a neighboring molecule is electron poor, and it developed a bunch of partial positives. So that's those instantaneous dipoles that are aligning themselves up, even in a hydrocarbon, which is completely nonpolar. Explain why molecules with more mass, or in other words, more electrons, have higher boiling points. So we just looked at butane on the last slide, which has 4 carbons in it, C4H10, and we're going to compare that to pentane, which has 5 carbons and 12 hydrogens compared to 10, and then hexane, which has 6 carbons and 14 hydrogens. So as we go from left to right, we are increasing in the number of carbons and hydrogens present, but really we're increasing in the number of electrons when we add all these bonds. So the London dispersion forces are going to get stronger as we go from left to right. All of these molecules we see here are all nonpolar. They all are only made up of carbon and hydrogen. And the difference in electronegativity between a carbon and hydrogen bond is so small that we can consider it to be about 0. So in butane, the boiling point is about 0 degrees Celsius. As we go to pentane, the boiling point increases to about 36. And then as we go to hexane, that's going to be also a liquid at room temperature. The boiling point is up to 69. So pentane and hexane are both going to be liquids at room temperature. We'll actually use these in the lab. And butane, with smaller London dispersion forces, is a gas at room temperature. Its boiling point is below about 25 degrees Celsius. So those London dispersion forces do impact molecules, especially when they're the only type of IMF that is present overall. Next, let's compare 3 more molecules and their boiling points with their London dispersion forces. So we want to explain why highly branched molecules will generally have lower boiling points. So starting with pentane, which pentane has 5 carbons in it, and it's going to be C5H12, so there's 12 hydrogens. The boiling point is around 36 degrees Celsius. This is what we would call a straight chain hydrocarbon. So all of the carbons are aligned in a straight chain, as you see. There's no branching here. Now, as we move to something like 2-methylbutane, notice what we didn't change. There's still 1, 2, 3, 4, 5 carbons, and there's going to be the same number of hydrogens. So it still is C5H12. So we have a little bit of branching. 3 of the carbons are in a chain, and then we have 2 that are branching off at the end. The boiling point decreased to 28 degrees Celsius. So we'll call this a little branching. And as we start branching, essentially, we're decreasing the surface area. So now looking at the one on the right, the far right here, 2,2-dimethylpropane. In this molecule, we have 1, 2, 3, 4, 5 carbons, and we also will have the same number of hydrogens, so C5H12. The boiling point has decreased even further down to 10 degrees Celsius. So this one in our example would have the most branching, or the lowest surface area. So as we decrease the surface area, so as we go from left to right here, we decreased the surface area of our hydrocarbons, and we also decreased the London dispersion forces present, which is why those boiling points continue to drop as our branching increased or our surface area decreased. And what happens is the decrease in that surface area that's present between those molecules now decreases the attractive force that can form between the individual molecules. So we have lower boiling points, or if they were solids, we would have lower melting points. So all of these intermolecular forces we talked about really impact the properties of organic compounds.